In 1905, Einstein published his paper on special relativity. Despite its massive impact on theoretical physics, it had just two postulates, two rules he proposed the universe had to obey. The first, the laws of physics are the same for everyone moving at a constant velocity. The second, light always travels at the same speed, about 300 million meters per second, regardless of who's measuring it. That's it. That's the whole theory, written on two lines. Relativity has a reputation for strange, counterintuitive outcomes, and that reputation is earned. But what I want to show you is that those outcomes aren't arbitrary. They follow inevitably from exactly these two rules. In order to see what these new rules imply, we need a tool, a very specific kind of clock. Imagine a clock built from nothing but two mirrors and a single photon of light. The photon starts at the bottom mirror. It shoots straight up, bounces off the top mirror, and returns to the bottom. That round trip, bottom to top and back, is one tick. Although it may feel strange at first to build a clock this way, if light is the one thing in the universe whose speed never changes, per Einstein's postulates, then light makes the perfect ruler for measuring time itself. Let's call the distance between the mirrors L, and we can call the speed light travels c. So the time for light to go up is L over c, back down is another L over c. One full tick takes 2 L over c. Simple, clean, and completely determined by the distance between our two mirrors. Now suppose that same clock is moving. It's gliding past you at some constant velocity while you watch from the side. The photon still has to travel from the bottom mirror to the top, but while it's traveling, the whole clock has moved to the right. So from your perspective, the photon doesn't go straight up, it traces a diagonal, up and to the right, then back down and to the right again. That diagonal is longer than the straight vertical path inside the clock we saw earlier. We can measure exactly how much longer with the Pythagorean theorem. Call the time for one tick as you measure it from outside just t. In that time, the entire clock has moved a horizontal distance of v times t. The vertical height is still L, so each diagonal leg has length square root of L squared plus the quantity vt over 2 all squared. As long as the velocity here is non-zero, we can quickly tell this path length is greater than the vertical path we saw earlier. And so, we now have two different tick durations for the same photon. From the at-rest perspective sitting next to the clock, 2L over c, the straight vertical path. From the perspective of watching the clock move past you, 2 times the square root of L squared plus the quantity Vt over 2 squared, all divided by c, the diagonal path. And so, it feels like we have arrived at a contradiction. These two tick times are clearly different, but the photon is the same photon, and according to Einstein, it must have traveled the same speed in both situations. To find the resolution here, let's quickly look back at the simple equation for distance traveled. Distance equals velocity times time. If the speed of light, the velocity in this case, is the same for every observer, but we measure different path lengths for the same tick, it must be the case that the time measured is larger. In other words, if velocity needs to be constant and distance increases, time must increase proportionally. Let's work out exactly how much it changes. To do that, we need to name our two times carefully. Call the tick time measured by someone at rest beside the clock t0, the proper time. Call the tick time measured by the outside observer who sees the diagonal path just t. To help us keep track, let's pin both results to the side. The stationary tick time t0 equals 2L over c. And the moving observer's tick time is 2 times the square root of L squared plus Vt over 2 squared, all divided by c. We'll refer back to these as we go. Our goal here is to understand how time changes between reference frames, so we are looking to solve for t in terms of t0 and any other relevant variables. We'll start by setting the two path lengths equal by using the geometry from the previous scene. Square both sides. Move the v squared term across. Now let's substitute 4L squared for the quantity c times t0 all squared, the result we derived for the stationary clock, and factor the left side at the same time. Finally, divide through and take the square root. There it is. T equals T0 divided by the square root of 1 minus v squared over c squared. Call that square root 1 over gamma. So T simply equals gamma times T0. Gamma here is called the Lorentz factor. This factor tells you by how much time has been stretched. When v is small, a car, a rocket, even a satellite, gamma is nearly 1. Time barely stretches, which is why we don't feel any of this in everyday life. But as v approaches c, the denominator collapses toward 0. Gamma grows without bound, and time dilates dramatically. Let's graph it. Look at the curve. Flat near 0, then it bends, and finally, we asymptotically approach v over c. For speeds that we are familiar with as humans, the effects of time dilation are completely negligible, accounting for nanoseconds of difference over decades of time. But for subatomic particles inside nuclear reactors or being ejected from dying stars, relativistic effects matter, and to us, their clocks truly tick slower. But it turns out that time isn't the only thing that has to bend. Let's go back to the equation that started all of this. Distance equals velocity times time. 3 variables. We've shown that if c is constant, time must change. But there's another option hiding in that same equation. Distance. Distance can change too. Think about it this way. We've shown time stretches, but the speed of light can't change. Speed is distance over time. If time gets bigger and speed stays fixed, something has to happen to distance too. The geometry demands it. To see this clearly, let's rotate our light clock 90 degrees. With the clock horizontal, the photon now travels in the same direction the clock is moving. This breaks the symmetry we had before, and that's exactly what makes it interesting. When the photon moves forward in the same direction as the clock's motion, it's chasing the far mirror as it moves away. That leg of the journey takes longer. When it bounces back, the near mirror has rushed in to meet it. That return leg is shorter. The 2 legs are no longer equal, but the total path, the distance light covers across both legs, still has to equal c times gamma times t0, the speed of light times the dilated tick duration we just derived. Working through the algebra, and I'll spare you the full grind, what you get is this. The length you measure for the moving clock is L divided by gamma. It's shorter. Gamma is always greater than or equal to 1, so L over gamma is always less than or equal to L. The moving object is shorter along the direction of motion, not because it's compressed by some external force, not because the atoms are squeezed together, but because length and time are woven from the same fabric. When that fabric stretches in one direction, it must contract in another. Understanding that fabric is a rather important point to drill into. At this point, it may feel like we have broken every basic law of physics you know. Lengths get contracted, time gets dilated depending on the observer. But I promise that hiding in this new relativistic world, there is still some invariance we can count on. One way you could conceptualize it is geometrically. Let's start by taking a basic look at a rectangle. Its width is the length of our clock, L, and its height is the proper time tick duration, T0. So, trivially, the area of this rectangle is just L times T0. Now let the clock move. We've shown that the length contracts to L over gamma, and the tick time dilates to gamma times T0. So, what happens to the area? L over gamma times T0. The gammas cancel, and the area is still L times T0. That product, L times T0, is an invariant. Notice it doesn't depend on your speed, so every observer in every frame agrees on this number. The geometry here is actually telling you something deep. Space and time aren't independent quantities that just happen to be related by a formula. They're 2 sides of the same conserved entity. Stretch one, and the other must compress to compensate. The universe is enforcing a constraint, and that constraint has a shape. So let's trace back what happened. We started with just 2 rules. Physics looks the same for everyone in uniform motion. and light always travels at the same speed. We built a clock out of mirrors and a photon. We watched it move. We refused to let the speed of light change, and the universe handed us, forced on us really, the fact that time itself must stretch and lengths must compress. Not as metaphors, not as approximations, as geometric consequences of how space and time are actually structured. Einstein didn't discover that the universe is strange. He discovered that the universe is consistent. And consistency, followed far enough, turns out to be the strangest thing of all.